in the context of Bayesian logistic regression. So in logistic regression, we have looked at the MLE term, which is given a data set like this, you want to create a linear separating hyperplane. And what we do is just write down the likelihood, which is just the multiplication of P of yi given xi and thetas. And we can then just substitute the P of yi given xi comma thetas coming from the, because of the Bernoulli likelihood. And if we carry down this expression, we will get the log likelihood to be the negative cross entropy, right, or the loss to be cross entropy loss. And we can then compute the gradient with respect to theta and solve for this. So if we compute the gradient to get the MLE solution, the gradient turns out to be x transpose sigmoid of x theta minus y. Right. Typically, you just want to set this to 0 and get the theta hat. You can't do that here because you will end up with terms which are log of y upon 1 minus y, and y is either 0 or 1. So, you will not be able to compute it this way. So, therefore, we end up computing the MLE via gradient descent like procedures. So, there is no closed form. We would be able to get a boundary like this, where we have a separating hyperplane, where the probability of class 1 is 0.5. So, is this plot showing you any kind of uncertainty, or is it just not, is it not showing you any kind of uncertainty? We discussed that there are two types of uncertainties.
Like the plot is showing uncertainty, and the color bar is showing the probabilities of classification of to be classified as y equal to 1.
Okay.
So, and the line that passes through the middle, there is a probability of going to either class as 0.5.
Mm-hmm. What kind of uncertainty are we talking about? No. We have not considered any uncertainty in the model. From the model, we are just obtaining a point estimate, which is the MLE estimate. So, if we are not considering any estimate, any uncertainty from the model, where is the uncertainty coming in from? Aleatoric uncertainty, or the likelihood term that we are looking in at. So, therefore, we have probability of points going from 0 to 1, right. So, we are looking at through the Bernoulli likelihood. We could have also used the map estimate, for which we will have to put a prior. Generally, we put a Gaussian prior. So, we can then compute the negative log joint term, which is just the negative log likelihood and negative log prior, they are added up. And then we can compute the decision boundaries using the map and compare it to the MLE estimate. So, I mentioned that the prior is weak. My prior was normal with mean 0 and the variance to be sigma square. Why would I call this to be a weak prior when sigma square is a very large value? Anyone? Okay. In a very large space, right? So, theta, we are saying that it is centered at 0, but it has a huge amount of variance. So, we do not really know anything about theta before we have conducted the experiment. And the MLE solution that we get is minus 0.695 and 1.422. What kind of relationship do you expect between the thetas obtained in MLE and theta obtained in map? How might you compare these? They are obviously different. How might we say that they are related? Okay, Ritik.
Map estimates will be
Closer to the mode of the prior, which is 0, right? So, if you look at the length of the theta vector, which is summation theta is squared, square of the length, and if you look at the square of length in MLE, you would see that the map solution's summation theta is squared would be smaller, which is the same effect as we have seen in the case of regularization, which is, so the prior is helping act as the regularization to ensure that we do not overfit. The same concept is being added here. With a different prior, now we'll see the values to be slightly different. And if we had a very strong, very specific prior that I know that my theta is going to be close to 0 only, then we can see that our data is not having much effect. Right? So depending on how strong the prior is or how much amount of data that you have, your map and therefore your posterior would move between the mode of the prior and the MLE solution. So in this case, we are very close to the prior because the prior is very strong. But in the first case, where the prior is very weak, we are very close to the data, the solution obtained by just looking at the data. Okay, so now we need to go the full Bayesian route. We would again have to compute the posterior distribution for logistic regression. So we have this term in the denominator, which is the evidence term, the marginal likelihood term. What distribution is P of d given theta? Bernoulli. What distribution have we put on P of theta? Gaussian normal. Can we integrate out Bernoulli times normal? Turns out we can't. So therefore, we cannot compute the denominator term. And we also know that they're not forming any conjugate pair, therefore we cannot integrate them out. So in the case of linear regression, we had this very convenient form, normal, normal, and the posterior was also normal. But here we don't have that convenience. So therefore we are stuck. What can we now do in order to compute the posterior? Approximate the integral. You could do two things. One, you could approximate the integral, right? So this you could do using Monte Carlo simulations, which we'll study today. But before that also we studied something in the previous class. If we are given an unnormalized posterior, can we approximate it with a normal distribution? Right? That was what Laplace approximation was trying to do. So in summary, what we saw in Laplace approximation was that we need to compute the negative log joint. Right? We'll get minus log p d given theta minus p of theta. So negative log joint is just the numerator term. Just considering the negative log of the numerator term. It is not considering the denominator term. We just assuming it to be a constant. We can compute negative log joint function f theta. We can compute its mode. We can compute the mode, which should now be the map, theta map. We just optimize this f theta function to get the theta map, and then we say our Laplace posterior is some distribution q of theta, which is normal in theta with the mean or slash mode to be theta map, and the covariance to be the inverse Hessian of the function f evaluated at theta map. Right? So this we discussed in the previous class. In the first slide, I showed how to compute the gradient x transpose into y hat minus y, something like that. We got that particular expression. So therefore, we can also compute this term, which is the Hessian. It will turn out to be slightly big term, but that can be computed analytically also. Or you just use tools like torch, JAX, TensorFlow, etc., to compute these terms in a computational gradient, in a computational graph. So at this point, we now know the posterior, the approximate posterior for Bayesian logistic regression, but we are not done. Right? The important thing is not just to give a posterior, it's to make predictions on new data set, on new data points, and give the uncertainty about it. So which always means that we are trying to solve an integral of this form, p of y star given equal to 1. So in the case of linear regression, we just used to write p of y star given x star comma d. But here because it's a classification problem, we are looking at p of y star equal to 1, p of y star equal to 0. So we'll write that as p of y star equal to 1 given x star comma d is the integral of, you have to introduce theta and you have to introduce out theta, integrate out theta. So bring in theta and integrate it out. You have to consider all possible values of theta which could have been considered, right? So we bring in theta and we bring in theta in the first term and bring in theta in the second term. What is the second term here called? P of theta given d is the posterior, but we don't know posterior. What do? We replace the posterior with the Laplace approximation. q of theta. The first term is known as the no, it's a simpler term. It's just the likelihood, right? So P of y is the data given theta, right? Given any specific theta, what is the likelihood of obtaining y equal to 1 and knowing x, right? So you'll always have the integration of likelihood and a posterior like term to obtain the new predictions, right? So we replace P of theta given d with Q of theta, which is coming from the Laplace distribution. This is an approximation that we've made. It's not exact. But Q of theta is normal. P of y star equal to 1 given x star and theta is Bernoulli. We're stuck with the same problem now. What do we now do? So one of the reasons why we did Laplace approximation was that we said that computing the integral we can't do. Right? If we could compute the integral, we would have just solved that. But we're stuck with the same problem. Right? So let me go back and show what I mean. So if we said that there are two methods to solve this. Let's assume in method 1 we say that we'll compute the integral in some way. Right? If we could compute the integral, we can obtain P of theta given d. Right? We said that let's for now assume we can't compute the integral. So we'd approximate P of theta given d to be a normal distribution. Right? It comes out to be normal distribution. But then we're again stuck because we get the same integral, normal times Bernoulli integral. Right? What can we now do? Someone else? Sorry? Laplace approximation of what? Of the integral. How would you do that? So Laplace approximation you generally use when you have an unnormalized posterior. So that is why I think we need to be a little careful with this. Laplace approximation we are trying to obtain for unnormalized posteriors. Another way to say the unnormalized posterior is to talk about the joint, the numerator term, which is, you can think of this as unnormalized posterior. We are trying to approximate P of theta given d. That is where you use the Laplace approximation. But here we have a different term. Here we have an integral I want you to solve. How can we do that? People? Right. So we'll use something known as Monte Carlo estimation. I'll first show the form and then we'll go on and see some examples for that. And this, by the way, P of y star equal to 1 given x star and theta, we just put in the sigmoid term and we can then compute likelihood. Technically, we should have put the Bernoulli around this and done it that way. So can we write this as the expectation of this term, sigmoid of x transpose theta under the distribution Q of theta, right? That is the standard definition of expectation, the relationship between expectation and integration. And this is where the Monte Carlo estimation comes in. We say that we can approximate this quantity of interest with a summation over any number of samples, here capital M number of samples, where the samples are drawn from Q of theta. Right? So this will take a bit of time to understand what it means by drawing a sample from Q of theta and substituting in it. Right? But this is the main flow that we'll be following. After we have done Monte Carlo estimation, we'll be able to obtain the predictive distribution. Right? So this is a very good example because it shows that first we could not compute the posterior. We had to take an approximation which we took as the Laplace approximation. Even with the Laplace approximation, when we are trying to compute the predictive distribution, we are stuck because again we have an integral which is intractable. So therefore, we end up computing the Monte Carlo estimation of that. Now, someone may suggest, you may think, why did you not just compute this integral through Monte Carlo sampling and put it over here? You can do that as well. You can compute this integral via Monte Carlo sampling. What is the difference between this integral that you're seeing and the integral that you see now? What is the difference between these two integrals? Or this integral that you're seeing versus this integral. One is using the prior, the other is using the posterior. That is the only difference, right? So technically, if you know how to solve one, you also know how to solve the other one. The method would be the same. You could have used Monte Carlo estimation. We'll see how Monte Carlo estimation works. Importantly, once we have taken the uncertainty of the model parameters into consideration, which means that now we're considering both epistemic and aleatoric uncertainty, we will be getting boundaries which are slightly different. So if we were to use Laplace, we'd get a boundary like this. So Laplace, sorry, if you were to use map estimate. Map estimate is a point estimate for the parameters theta, and based on that, we get uncertainty, which is only showing you the differences in probability for the different points in the space. Whereas for the first one, we have used the Laplace approximation, and then we have taken the predictive distribution using Monte Carlo sampling, right? So we'll get the we'll get the predictive distributions to be something like the following. Does this start to look a little bit weird, little different compared to what we are seeing in the map or what you've seen in MLE? So it seems that the decision boundaries are following non-linear contour lines here in the above plot, whereas in the bottom one there doesn't seem to be the case, right? How can you explain that?
The reason for non-linearity is because as we go further away, further apart from the data is between -8 and 0. If we go further apart, then the uncertainty of the prediction should be higher.
So I would just say that this is coming in, I would just simply say that this is coming now because you're also considering the uncertainties in theta themselves, right? So individual for any given theta, the boundary would always be linear, right? But the theta themselves have some amount of uncertainty, they themselves have some amount of distribution. If you factor that in, you'll get something like this, right? So if you were to consider a simpler variation of this problem, instead of directly showing you this result, I were to show you different thetas I had drawn from the posterior. So we have this expression, right? So let's assume that my posterior is q of theta, or it's just p of theta given d. I can draw samples from it. Any given sample, once I use that sample, I get a straight line, right? But my samples are themselves coming in from a distribution, from a normal distribution. Because of these two compounding effects, you may get decision boundary which looks something like the following. Right? So at this stage, we are looking at both the aleatoric as well as the epistemic uncertainty. This will become clear once we see the simpler case, which is linear regression. Logistic is slightly harder to understand in the first go. Any questions on this? There are other examples also. If we use a medium prior, if we use a strong prior, and the decision boundaries would somewhat change. Yes.
In this case, can we say that the uncertainty depends upon the input x actually? So we can say that this
So the likelihood is still homoscedastic, right? You have, oh sorry, so let's see. The uncertainty is not as a function of the input. The uncertainty is an input. So in this case, because of the varying thing that you're seeing, that is because of the model parameters theta, and not because of. So once you choose a theta, you'll always get a straight line, and you'll get equivalent similar lines as we're seeing in the below plot. So let's just wait for a few minutes, and we'll first see the case for linear regression, where this will become easier to understand. Other questions? Okay, so now we come on to Monte Carlo sampling, which is my favorite topic in this course. So there's a bit of history for Monte Carlo method. So whenever we discuss this topic, we do end up discussing the evaluation of pi. But if you look at the history, you'll see some terms, some names you might have heard earlier. 1940s, Stanislaw Ulam invented the modern version of Monte Carlo, Markov chain Monte Carlo. Enrico Fermi. Does anyone remember Fermi, of where you might have heard? There are particles known as fermions, right? So Fermi was also involved in the Los Alamos National Laboratory in the Manhattan Project for the atom bomb. Ulam was also there, so they were looking at neutrons, diffusions, etc. John von Neumann, right? So all these scientists were involved in the initial setup of the Monte Carlo method, and I think one of them gave the name Monte Carlo because I think one of their uncle used to go to this place Monte Carlo. It's a place where you have a lot of these casinos, etc. Because it resembles a game of chance. So therefore, they named it as the Monte Carlo method. So if you know about the F1 racing, does anyone here follow F1 racing? So there is also a track in this, which is known as the Monte Carlo track, Monaco, I think. So it's the same place, Canfield Solitaire, etc. But it's important to know that many of these things were initially set up during the wartime itself, right? And they helped them to create a lot of the nuclear physics that we study these days. I believe this is the same person after whom the language Stan is named after. So there is a Stan. It's a probabilistic programming language. I believe it is named after him, but I'm not fully sure. Right. Stan is named in honor of Stanislaw Ulam. So it's one of the most popular packages for probabilistic programming that you'll see. It also allows you to very cleanly specify different programs. So if we can perhaps look at a very simple example, we'll see. Right, so it gives you full Bayesian statistical inference with MCMC sampling, approximate Bayesian inference with variational approximation, etc. And they'll have some okay. So the same linear regression example which we saw a long time back. You can specify the priors. You can specify certain amount of ranges. For example, they are mentioning that you have data, which is the number of data points is n, but it is an integer, and the lower value of it is 0, so it's a non-negative integer. You have parameters alpha and beta, which are real. You also have a parameter which is sigma, but it's real with lower value equal to 0. And then you have a model which is y is given as normal of alpha plus beta into x plus the variance plus the scale sigma. So it's a very well used package for probabilistic programming. So a lot of the roots go back to the early 1940s and 30s. So in Monte Carlo methods, we are trying to compute very hard integrals, which we cannot compute analytically. So typically we end up computing integrals of this form, integral of fx, px, dx, which we can also write as the expectation of fx under the distribution px. Right? Both of them are important same terms. And what we are saying is that we can compute this above integral by extracting samples from p of x, sampling from p of x, and then converting this integration into a summation. Right? So these both are considered to be equivalent. So a lot of people write this particular expression, the second equation, but they often miss the last bit, which is important, where xi is distributed from p of x. Right? So the samples are drawn from p of x, and then you just get in a sample and plug it into f to get f of xi, and then you just take the average over n examples. It is really a very simple definition of this method.
So how big do we have to keep and do
I didn't get your question.
how big the number of samples should be?
Yes, we'll see that. The question is how big should the number of samples will be? We'll see in a few minutes. The important thing is that Monte Carlo estimates are unbiased. So even for a small sample size, you would be, on average, you would be around the mean, around the true value. But they have variance which will depend upon the number of samples. As the number of samples increases, the variance will reduce in the estimate. I think it's easiest to start by looking at computing the value of pi. Right? How might you use Monte Carlo methods to estimate the value of pi? So go back to the original definition. You're trying to compute some integral fx px dx. Right? We know the area of a circle, of a unit circle, is pi. Right? We can perhaps just look at a unit square within the quarter circle. Right? So how might you think about solving this using Monte Carlo methods? Importantly, for Monte Carlo methods, you only need to define two things, fx and px. There are two ways to think about this. One, let's take the non-mathematical way. Let's intuitively think. Let's see that you had this unit square. We are only considering the first quadrant of the circle. Right? We consider the first quadrant, and you're throwing darts into the square. Right? Throwing darts into the square, throwing sand particles, whatever. And some of them will fall in the green region, some of them will fall in the red region. Right? So what we're saying is that pi over 4, because the area of the entire circle is pi, area of a quarter circle is pi over 4. We're saying pi over 4 is approximately equal to the area of the green part divided by the area of the green plus the red area. Right? Now, what we're saying is that in order to get an estimate of these areas, we'll say that so what we said here was that we are drawing darts, we're throwing darts. In what space are we throwing the darts? 0 to 1 on x1 and on x2? 0 to 1, right? Can we say that we're just throwing darts from a uniform distribution? Right? We're trying to capture the entire space. We're not looking at any special distribution which has mass around the center, etc. We can just use the uniform distribution. That becomes your p of x. Right? And then what we're saying is that we can have fx, which is an indicator function, which is green if my dart falls within the quarter circle, or it's a red or a 0 otherwise. Right? Each time I throw a dart, it falls within the circle, I count that, and I know the total number of trials. Right? So the number of darts which fall within the green to the number of total darts is my estimation of pi over 4. Or if you want to put the previous thing more mathematically, you have x1 and x2. So for any x1, x2 that you draw from uniform in 2 dimensions, you can look at x1 square plus x2 squared. If it is less than 1, we put a 1, otherwise we put a 0. Right? So this is just the function telling whether or not we are within a circle or not. Right? So we can also write fx equal to an indicator function, which is x1 square plus x2 square less than equal to 1. Right? 3 different ways of solving the same thing. One was just using simple color notation. Second is just putting it mathematically. And third is making it more succinct function using the indicator function. Right? That is it to the Monte Carlo method for estimating pi. It's not a very sophisticated algorithm. And I think this becomes interesting once we start coding it up. So then all what we're trying to show is We know the true value of pi, which I've said is torch.pi. This is having certain finite amount of precision. Maybe we could have used more. So this function is all we need to understand now. We are setting in the manual seed, we're setting in a random seed. We are drawing xy, we are generating n points in 0, 1, 0, 1 unit square, right? Or we are generating n points from a 2D uniform distribution between 0, 1, 0, 1, right? That is what we're doing. We are computing x1 square plus x2 squared, right? x1 is just xy, all the points 0th dimension and all the points first dimension. We can check if this distance is less than equal to 1, right? If it is less than equal to 1, we get a true, otherwise we get a false, right? So for points inside, we can just see the sum, right? The number of sum of this is going to be returning 0 or 1, right? So you'll just get a sum of the number of, you'll get the sum corresponding to the number of points which fall within the circle, and then your estimate for pi is just number of points inside which fall within the circle divided by the number of draws that you have done into 4.0. Why do we have this into 4.0 term? Because we are trying to estimate pi by 4, right? And this is all we have in this function. If you wanted to make it actually little more accurate, you could have just, instead of torch or trend, while it's computing from the torch or trend directly gives from the uniform distribution, but I would recommend using torch dot distributions dot uniform and then generate it and then just use it x1 x2. If you want, you can use the norm etc. to compute the distance, but essentially this is the function. Someone asked, so Ritik was asking, how many samples would you need, right? How many samples do you think you'll need to from this to get a good estimate of pi? So actually let's try and see this in action also. I will write a bit of code for this. Let's say n equal to 10 and seed equal to 42. So we get this. We get these 10 samples, right? For each of the sample, now you can see whether x1 squared plus x2 squared is less than equal to 1. So I can just, to make it easier, I can write xy of 0, 1 and x2 equal to xy of, and you can compute distances equal to x1 squared plus x2 square, right? And we can just then look at distances comma x1 comma x2, right? So some of these values 0.76, 0.83, 0.95, some of these values are less than 1, some of these values are greater than 1. What you could also do is to plot them using different colors within a circle. So we could also do plt dot plot. So we could first just plot, we should not, okay, what we have done is we could have just done a scatter. Right? These are all your set of points, right? And we want to be then able to just color these points differently based on whether the distance is within or outside. So let's say distances, let's say c equal to distances less than 1, and if we print c, right, so it's false or this, so we could then perhaps do c equal to c dot float, Let's see if this works or not. Right. So now you can see that all these yellow points are falling within the circle. The blue points are falling outside of the circle. That is all you needed to do. But you only had 10 points. You can also see the value of pi that you get here. So that would just be the number of times, and this divided by n, the whole into 4. So we are getting 2 over here. It's a very poor estimate. If we had n equal to 50, 3.04. If we increase n to 500, now can you see the pattern? You're throwing the darts and you're now filling in the. Now the value is 3.131. So for 5,000 draws, the value still seems to be very inaccurate. Right? You've not got 3.14 also for 5,000. $10,000 you get 3.146. Third decimal place is still wrong. Right? But this is the main idea. So therefore, at least for something like Monte Carlo sampling, I would always suggest you just write a bit of code. That's the whole point of Monte Carlo sampling, that you can write 5-10 lines of code and you can get good answers very quickly. Now what we wanted to see was for different sizes of the data set. So I'm looking at 10 to the power 1, 10 to the power 2, 3, 4, 5, 6, 7, 8. I want to compute the value of pi, and for each sample I'm using different random seeds to ensure that I get some variance. Right. So it takes a bit of time because I have samples of the size of 10 to the power 8. And you can see this kind of table that I've got. Right. So for the first seed, n equal to 10, the estimate is 3.2, 3.2, 3.14, 3.139. So even for this 10 to the power 8, right, it seems that we have not got the fourth digit correct. It should be 3.14159265535. I don't remember beyond that, but so 3.141 is correct, but this decimal place is wrong. And then what we wanted to see was to look at, you fix n and you look at the different seeds, and then you can compute the mean and the variance. Right. So this is the same thing as you have been doing in the earlier assignments. So I'm just grouping by n, which is my datasets, my sample size, and I'm aggregating over mean and standard deviation. So I'm computing both, and I'm just looking at the pi estimate. So it will give me a table something like the following. So you can very clearly see that the standard deviation goes down as you increase. The mean will get closer, but the mean, as I'm mentioning, is, so the estimate is an unbiased estimator. Right? On expectation, you'll get the correct answer. So then I also wanted to show the estimated value of pi versus the sample size. Importantly, I've put the sample size as the x-axis in the log scale. Right? You can see there is huge amount of variance for small number of samples. And the dotted line is showing the true value of pi. So it seems that we have got a very good estimate. There is no uncertainty. Right? Does that seem to be the case? There is absolutely no variance, right? Beyond 10 to the power 5, so 10 to the power 6 onwards, it seems it's a very good estimate. But are we missing anything? Why are we not able to see that variance? Yes, excellent. So then what I did was, I only plotted 10 to the power 4 and higher number for this number of samples, and I put the y scale, y axis also in the log scale. And if we do that, now can you see that, and I've plotted this true pi plus minus 0.0001, right? And you can see that there is, for even 10 to the power 8 samples, we are roughly on that order, on 0.0001 error that we're making, right? So now go back to the start of the lecture and see how Newton was able to compute all of these terms without using a modern computer to much more precision. So 10 to the power 8 is a lot of computations. Any questions on this? What? Okay. So at the start of that particular video, they were mentioning that for some it's just mathematical. You just want to show your mathematical strength or your computational strength. I don't know if there are some very specific applications, maybe space applications, which require you, or some applications where the precision is indeed needed. I am not aware of. Does anyone know any specific applications where you require a very high amount of precision for pi? Sorry. Mm-hmm. Okay, so
Mostly the scientific constants like the Heisenberg constants consist of pi. So we will fine tune the calculation.
okay, so what he's saying is that there are other constants which also depend on pi, so you need to have pi to be very, very accurate. Okay, so even for LIGO, even for space satellites, they're mentioning that you require a higher amount of precision. But we are not going to be using Monte Carlo for showing off that what we can compute pi values. I will also share an article which there was on TensorFlow blog, a Google blog, which was showing that they've beaten all the records. They've computed it to some million digits, something like that. And I also want to think, I'm not fully aware of how they may even go about checking whether it's correct or not. So they need a true reference value also, but I'm sure there would be some benchmarks which have been set up. But anyway, coming back, so we now know how to compute integrals, complicated integrals. This was a very easy integral. You could have just used simple calculus and got the answer correctly. But then we wanted to compute more complicated integrals. So specifically, we want to be, so in Bayesian logistic regression, we discussed this, right? We want to compute this integral, p of y star equal to 1 given x star and theta, d theta. This is our posterior. For logistic, we replace it with our approximation, right? But let's look at some code where we're trying to generate the predictive distributions. So one important thing to see here is that here we're using the posterior. So therefore, this is known as the posterior predictive distribution. You could have also used the prior, and then it will be called as the prior predictive distribution. But the calculations, everything would remain the same, right? So therefore, just to showcase how this works, we'll look at a simpler distribution first, which is a simple problem, which is linear regression, and we'll first look at the prior predictive distribution before we look at the posterior predictive. So I am looking at this simple linear regression problem. We have only two parameters, theta 0 and theta 1. I have to specify my prior mean and covariance. I am specifying my prior mean to be 0, 0 and my prior covariance to be 1, 0, 0, 1. Right? What kind of a covariance is that? Spherical. Right? My theta, so theta, my theta here means the prior distribution, is a multivariate normal with the prior mean and the prior covariance. Right? So nothing sophisticated till this point. We can also just verify what we get. We can also plot the contour plot corresponding to the prior, and we've been doing this for a long time now. We can get some samples from the prior distribution, right? So in this case, I'm just calling theta dot sample, and I'm generating 1000 samples from it, right? So first, let me actually show you what these samples might mean. So this is how my different samples would be. For each sample, I am plotting a black dot. As you'd expect, there are a lot more samples closer to the mean, and as you move away from the mean, the number of samples would be lesser, right? So this is what it means by drawing samples from a certain distribution. We have done that already, right? So we have this. So what I'll do is, I will pick up one such sample, let's say minus 0.18 and 1.12, right? Corresponding to this one value of theta naught and theta 1, I can draw a line, right? Because I know my equation of the line, which is theta naught plus theta 1 into x, right? So I'll start with the first value of theta and plug it in here to get a first value of y, right? Given an x, I can take the next value, I will get a different y. I can take many such values and I will get different y's. That's essentially what I am doing. I am considering this linearly spaced data from minus 5 to 5, and corresponding to each of the samples of that I have generated from this multivariate distribution, which is my prior, I do theta naught plus theta 1 into x. Right. If I do this and I just plot the different y versus x plots, right? Each of them is a line, right? If this is not clear, let's view for smaller number of samples. Each of them is a line, right? Now, if we just increase the number of samples to 1000, right? We get a predictions which look like the following, right? Now, if you were to forget about the way we have generated this, you might again think that we don't have this surface that we're looking at is not linear. Although it's created from a bunch of lines, it looks slightly non-linear, right? You have this parabolic shape, right? This was exactly what was happening in the previous case for logistic regression also, right? We have just lines only, just because most of the lines will go through this 0 0, right? Why will all the lines? Why would the lines be going through 0 0? Because that's the mode of your prior. That's the most likely value. So what I've then done is, I can take a mean of my y's, right, across all of these, and I can get a standard deviation. So we fix an x, let's say x equal to minus 4. You look at all the y's that I obtain for that, I can get a mean of that, and I can get a variance across that, right? So that is what exactly I'm doing, and I can compute this mu plus minus 2 sigma, right? So I have this my mean prediction, and I have my standard deviation, which is, you can also see it's being reflected. So this is my prior predictive distribution. Why is this my prior predictive distribution? So I'm trying to compute, right? So this, from the Maths for ML book, you can also verify this. P of y star given x star equal to normal of x transpose theta, right? X transpose theta. M naught is just the mean of the prior. So x transpose M, you can put x transpose M naught plus the covariance term, right? And there is a sigma square term. For now, I just kept sigma square to be 0. So I'm not considering any likelihood noise. I'm only considering at the variance which is coming in due to the model uncertainty, only the epistemic uncertainty. So it comes out to be x transpose S naught x. Right? That's the covariance that you get, and this is the closed form that you get. What we're saying is that somehow we're not able to compute this, right? If we go back to the lecture, this would have been our So this was the posterior that we obtained, but we said that we wanted to find out the posterior predictive, right? So in posterior predictive, we have P of y star given data comma x star, which is again the same integral we've been seeing, integral of P of y given x and theta, and then P of theta given d theta. And this we said is coming out to be something like this: normal with x transpose mn and x transpose covariance x star plus sigma square, right? We have now looking at the same expression, but instead of the posterior predictive, we're looking at the prior predictive. So therefore, all the mn and sn you can replace with m0 and s0. Everything else remains the same, right? So what we're saying is that this particular integral, if you're trying to calculate for certain kinds of problems like linear regression, we have this closed form expression, right? But again, can we solve this using Monte Carlo estimation, which is what I showed? You had P of theta, we had this prior theta, right? We generated samples from this. This was theta, and you generated samples from it, P of theta, right? And you just put those samples in f of xi, right? F of xi is P of y star given x star and theta, which is just a likelihood term. For linear regression, that is just theta naught plus theta 1x, right? I know the normal distribution about this, so I'm just assuming it to be the noiseless case. So it's just x transpose theta. Right? That is exactly what we're doing here. For every sample, you just put in theta naught plus theta 1x, and you do that for all the samples. And after that, you will get multiple such predictions. Now you can just take the mean and the standard deviation across these different samples that you've obtained, and you can say that that is going to give you the same result as if you use the closed form. So in this case, I'm using the closed form. I'd be able to get fairly similar results using the closed form, which required me to know the integrations. Right? But in MC sampling, I didn't need to know any integrations. I just sampled from the prior, in this case the prior, and I just put that into my likelihood, and I obtained different y's, and I've just plotted x versus y. I'm getting some confused looks. Questions? So the procedure is as follows. I'll just repeat. You need to know, you are trying to solve problems of the form. This is the general problem that you're trying to solve. P of y given x, it's an integral of P of y given theta and x and P of theta d theta. Right? So what you do is you get some samples from P of theta. For our example, P of theta was a multivariate normal, which was just the prior. Right? You get samples from that. The samples you plug in the first term, which is P of y given theta and x, which for our case was just a normal distribution with theta naught plus theta 1x. And with the variance sigma square. For now, for simplicity, I've just removed the variance sigma square, and I'm just considering it to be point estimate. So essentially, you can replace this integral, and you can get a distribution of P of y given x empirically from the samples. That's all we're trying to do. This was prior predictive. If we had to do posterior predictive, we can change P of theta with P of d given P of theta given d. That is the only thing which will change. And the other interesting thing about this is, so this was a very simple example where we know the closed form. But what if my distribution, my prior was a mixture of Gaussians, not a single Gaussian, but a mixture of Gaussians, which looks something like this now. Right? So the way I have generated this is, I have a Gaussian 1 whose mean is 0, 0 and covariance is 2, 0.5, 0.5 and 1, and I have a second Gaussian 3 minus 2, 1, 0, 0, 2. And I have added them in the fraction 0.7 and 0.3, the ratio 0.7 and 0.3. So I'll get a mixture of Gaussians, which looks like the following. Right? So what I'm saying is that now you can use this mixture of Gaussians as your prior, right? And now you can't compute the solution analytically for the posterior or the prior predictive distribution. But again, all you now need to do in order to obtain your prior predictive is to get samples from this distribution, which is the same as what you did previously. Get the samples, put them in the fx function, and you'll get y's. Just get the empirical mean and covariance variance, and you're done. So now you can. So now I've shown with mixture of Gaussians. I could have also put in the posterior, and the same procedure will follow. So that's the beauty of using Monte Carlo estimation. You can compute any integrals of this form: p of y given x is equal to integral of p of y given theta x p theta d theta with a summation. Okay, any questions? Someone was asking about the syllabus. So I think it would be not very fair to put this lecture in the exam. It's better to give you some more time. So the syllabus for the first quiz is everything we did till the previous lecture, till Monday's lecture, not today's lecture.
How do we decide when to use prior predictive or posterior?
So we decide when to use prior predictive and posterior predictive based on what is being asked from you. So you're making prior predictive when you don't know, when you have not observed the data. So then what does the distribution look like in your outputs? That is prior predictive. But once you've observed the data, you'll get posterior predictive.
But there are, we don't prioritize any of it based on computational.
No. So computational perspective, it's exactly the same. You just need to get samples and you need to put them in the likelihood.
This
Okay.
process of introducing and then integrating output as one margin.
Yes.
margin.
Yes.
So what allows us to do this?
What allows you to do what?
Like, is there a reason that doing that has no change?
Doing what has no change?
On the P, Y, Y given
Are you talking about the equivalence between 4 and 5?
X? No. Are there any rules that allow us to write equation 4?
Yeah, rules of probability. We'll discuss them in some other time. 2-3 different rules that we'll again discuss because they occur very commonly. For now, just assume that this was known, but we can discuss that if this is a question which is coming again. Okay, thank you everyone.